All right, this is the second video about equilibrium. We're still looking in chapter 13 in OpenStax. When we last were speaking, we were talking about this equilibrium right here involving 2SO2 plus O2 in equilibrium with 2SO3. We talked about how we could write the Q expression for that by just taking the products, raising them by their coefficients, dividing that by the reactants raised to their coefficients, and you're multiplying each of those together. So there's SO3 squared on the top, SO2 squared times O2 to the first on the bottom. And that when we reach equilibrium, that reaction quotient Q is equal to K. In version A here, we're starting from no SO3. If you look up here, you see that's 0. Here we're starting from all SO3 and approaching the equilibrium from the other direction. So no matter which way you start it from, you wind up at the same equilibrium. So that's the point of that. So, and again, this is this figure 13.5, slide 17, the color version of that is above there. And so what we say is that when Q is equal to the equilibrium, the value of Q that's present at equilibrium is equal to the equilibrium constant K, and when we say K sub C here, and we're raising again, taking the products, concentrations, raising them to their coefficients, and multiplying them together, and then dividing them by the reactants, concentrations, raised to their coefficients, multiplied together on the bottom. And again, this is called the law of mass action, and that's one of the fundamental skills is to be able to write this for an equation. They say here, don't confuse this with the kinetic rate constant. That would be written as a lowercase. So if we talk about K for a forward reaction and K for the reverse reaction, those rate constants, if we look at the ratio of forward to reverse, that's equal to the equilibrium constant, it turns out. Not something we'll use a lot, but it again does show that relationship. So again, the deal is this can be calculated at any set of values. And this one is only true at equilibrium. And sometimes as a shortcut taking notes, you'll just write the equilibrium sign for the word equilibrium. Okay. So if we look at the value of Q, okay, what we're going to see, well, this gets back to what we said, on the intro slide. Again, K is very small. That means that the reactants are very favored. If K is very large, that means that the products are favored. And if they're equal, they're about the same, and that the actual value of K gives no indication as to whether a reaction is fast or slow. So we don't know how big this hump in the middle is here. It could be, that it's really, really big, and of course the bigger this is, that determines this is E sub A, and we could write that in either the forward or the backwards direction there. And the E sub A determines rate back in the kinetics chapter, which is when we have those together. So this would be faster because it has a lower E sub A, and this would be slower. But we can't see that from the value of K, which simply is talking about the relative positions of what we're calling R and P here on this reaction coordinate diagram. So if a system's not at equilibrium, it's going to proceed in a direction that establishes equilibrium. And if we look at the value of Q and we compare it to K, we can determine which direction we have to go. So if Q is less than K, that means that the number on the bottom here is too big and the number on the top is too small. So we've got too many reactants. Too few products. So we're going to shift towards the products. to reach equilibrium. When Q is greater than K, then we have too many products, too few reactants, so we shift back towards the reactants. And when Q is equal to K, we're at equilibrium. No shift happens. Okay, so we're going to use Q. I call it a test statistic to determine which way you go, which way you have to go to reach equilibrium. So they're talking about this equilibrium here. This happens to be called the water gas shift reaction. You know, reactions sometimes have names. The importance of this reaction is that if you take that H2 and CO, those two things today can be made, you know, to make synthetic alkanes. Essentially, synthetic hydrocarbons are it's a way to make for example, gasoline without having petroleum to make it from, or to isolate it from. Anyway, so they're looking at the water gas shift reaction here, and they talk about you could start different ways. So if you started with just CO and H2O, then initially Q would be, you know, the top would be 0, right? You'd have, so for this one, if we wrote Q for this, it'll be CO2 to the first, H2 to the first, over CO to the first, H2O to the first. So in this case, I'm going to have 0 times 0 over something that's not 0. Well, that Q is going to be 0. That's going to have to be less than K, whatever K is. K is not going to be a negative number. K is always going to be a positive number. If I look at this case, if I start with just CO2 and H2, then Q is going to be some number. I don't know what it is. I'll call it N for CO2 and H2. The bottom, though, is going to be zeros, and anything divided by 0, that's infinity. And infinity has got to be greater than whatever K is, so that's going to proceed back towards the reactants. And then mixture 3, if we started with that, we don't know what those values are. Depending on them, we could determine which way it would have to shift. We'd also have to know the value of K. So these graphs here, this is the color version of this graph that talks about how we start with this, and you got to follow that. So basically, mixture 1 here goes to mixture 1 there. This is at equilibrium. This is before the reaction starts. And you got to follow your colors here. This is CO, this is H2O here. So we start with just CO and H2O, and you see that those do indeed go down when we reach equilibrium. They go from 0.0243 to 0.0135. And that we have the grow in of the CO2, which is the green color, and H2, which is the tan color there, maybe brown color. And anyway, so you look at all three of these reactions, and every time the K value comes out to be the same thing, this 0.640. K is dependent, is really dependent only on temperature. So these are all being done presumably at the same temperature. And then over here you have your Q's. Like I said, this was the Q is equal to 0. That's the one that we did up here on the previous slide, right there. And then the Q equals infinity one we did right there, just so you can see how that all ties together. And so that's the black and white version of that. Some terms, homogeneous, it means the equilibrium is all in the same phase. Most commonly, that's either in some kind of liquid or gaseous phase. you can include in your reaction quotients things are going to be concentrations for anything that's dissolved. Usually you can also do it for gaseous stuff. Pressure terms only for gaseous, obviously, but you can do concentrations of gaseous things. And if you express everything in terms of concentrations, it's Kc. If you express it in terms of pressures, it's Kp. So looking at the reaction that we were just looking at up here, Kc would be concentration CO2, concentration H2 over concentration CO times concentration H2O, all to the first. If I did K sub P, I would say partial pressure of CO2 times the partial pressure of H2, both still raised to the first power, divided by the partial pressure of carbon monoxide times the partial pressure of water. So that's how the Kc and Kp differ, just in terms of the use of concentration versus partial pressure. So if we look at this one we definitely do Kc for this. When you have a pure liquid or a pure solid, we leave those out of our Q or K expressions. So K for this, Kc would make the most sense. That's going to be H3O plus, which is called the hydronium ion, times F minus, the fluoride ion, both of those raised to the first because the coefficients are 1, divided only by HF. We leave H2O out because it is a pure liquid. And this we're going to see later on that this is an acid, and we're going to find out that this is called Ka for HF. We'll be spending a lot of time working things like that. Now the second equilibrium here, we have C2H6 giving up 2 hydrogens, which become H2 and becoming C2H4. We could do a Kc or a Kp there. Kc would be the concentration of C2H4 times the concentration of H2 over the concentration of C2H6. Or we could do a Kp, which is the P of C2H4 times the P of H2 and divided by the P of C2H6. Like so. Again, nothing's raised to any powers because the coefficients are all 1. So they're all being raised to 1, which we don't bother to write. If you try to relate Kp and Kc, you go back to the ideal gas equation here and you rearrange it so that you've got molarity and pressure, right? Remember, so this is saying that pressure is equal to molarity times RT. And what that lets you do is to derive an expression here for Kp and Kc, where Kp is equal to Kc times the RT from the gas law raised to delta N. This is a delta. And delta N is the change in the moles of gas. So you have the sum of the moles of gas of your products minus the sum of your moles of gas of your reactants. So if I have something like 3CO gas in equilibrium with C3O3 gas, delta N sub G here will be 1, there's only 1 gas on the product side, minus 3, there's 3 gases on the reactant side, so that's going to be a delta N sub G of -2. And the values of R and the temperature specification that it's got to be in Kelvin are there. So again, in heterogeneous equilibria where you have different phases, you leave out the pure solids and the pure liquids. So up here, you would not include this NH4Cl in this. So our Kp for this one would be PNH3 times PHCl, and our Kc would be concentration NH3 times our concentration of HCl for that one. And so what that means is that the equilibrium position is independent of this as long as at least some is present in the mixture. But we don't have to worry about it. Okay, moving on here to Le Chatelier's principle. We're going to talk about how you can stress an equilibrium, what's a stress, what is exactly a stress, and how that equilibrium